Hello everybody, welcome to the Ultimate Physics channel. The topic of this video is solving problems on mass energy equivalence. That is the very famous equation E is equal to mc squared. Based on that equation, we're going to solve some very interesting problems in this video. Before we start doing the problems, let us do a quick recap of the concept of mass energy equivalence. Based on his postulates of special relativity, Einstein gave science its most famous equation E is equal to mc squared, which expresses the mass energy equivalence. Though the equation looks simple, its impact is very profound in all areas of science. The relativistic expressions for total energy, kinetic energy, and relativistic momentum have intimate connection with this expression. Already we have done separate videos on problems on total energy as well as relativistic momentum. Please do check out the lecture videos as well as the problem videos on these topics on this channel. Now, the idea of mass energy equivalence draws on the concept that mass and energy are two aspects of the same thing called mass energy, and since these two quantities are not separate, their conservation principles must not be separate either. This equation tells us that whenever mass is created or destroyed, an equivalent amount of energy simultaneously vanishes or comes into being, and vice versa. That is the idea of mass energy equivalence, and it is useful to remember the following few points for solving problems on mass energy equivalence. E is equal to mc squared. First, the idea of the unit conversion between the electron volt unit and the joules unit. 1 electron volt of energy corresponds to 1.6 times 10 power minus 19 joules. And we commonly use the unified mass unit for mass rather than kg in many of the problems. So 1 U, the symbol for that is U. So 1 U is equal to 1.66 and 054 times 10 power minus 27 kg, which is equal to 931.5 MeV over C squared. In MeV over C squared units, the mass is 931.5 for the basic unit of unified mass units. There is 1 U. The mass of the proton, the mass of the neutron, and the mass of the electron or some required quantities worthwhile to remember. The mass of the proton is 1.007276 U. For the neutron, it is 1.008665 U, and for the electron, it is 0.000548 U. Let us move on to do some problems on this topic. The first few problems are basically going to be warm-up exercises. Then we move on to more challenging problems. The first problem is, what is the SI equivalence of the energy unit MeV and the mass unit MeV over C squared? We know that 1 eV is equivalent to 1.6 times 10 power minus 90 joules. So 1 MeV is equal to 10 power 6 times 1.6 into 10 power minus 19 joules. That is 1.6 into 10 power minus 13 joules. This is basically 1 MeV in SI units. That is 1.6 into 10 power minus 13 joules. This is the first part. The second part of it I deal with is 1 MeV over C squared in corresponding mass units. So that is, again, I directly take this value which I calculated above, that is 1.6 into 10 power minus 13 joules is MeV in equivalent in energy is this over C squared, so that is 9 into 10 power 16, 3 into 10 power 8 over whole squared, This is meter square per second square units. And if I simplify this, of course, joules is kg meter square per second square. So we get the value, the answer in kg units directly because of this cancellation. So if we work this one out, we get about 0.177 into 10 power minus 29 kg, or I can write 1 MeV over c squared is 1.77 into 10 power minus 30 kilograms. So that is the SI equivalent of 1 MeV over c squared. What is the energy of a photon whose momentum is the same as that of a proton whose kinetic energy is 10 MeV? So here we are comparing the energies of a photon and a proton. And what is the energy of a photon that is being asked here? We are comparing the momentum of a photon and the proton. Then again, the proton kinetic energy is given to us. So we know the expression in kinetic energy, that is in special relativity, the kinetic energy is given by gamma mc squared minus mc squared, because the total energy is gamma mc squared. You subtract the rest mass energy from it, you get the kinetic energy, and this is given as 10 MeV. And therefore we can directly write gamma minus 1 times mc squared is 10 MeV. The rest mass energy for the proton is mc squared is equal to 938 roughly MeV. This is for the proton. And therefore here we can directly substitute 938. Gamma minus 1 times 938 MeV is 10 MeV. So gamma minus 1 is 10 over 938, and that turns out to be 0.011. So gamma is 1.011. That is the gamma factor for this thing. Now once we know gamma, we can find the velocity of the proton moving at that with that gamma factor. If I do that here, 1 over square root of 1 minus u squared over c squared is equal to 1.011. So 1 over 1.011 is equal to square root of 1 minus u squared over c squared. And solving this and getting squaring the answer, I'm going to get 0.9895 on the left side. The right side, the square root remains 1 minus u squared over c squared. In the next step, if I square this up, I get 0.979 is equal to 1 minus u squared over c squared, and therefore I get finally u as 0.1449 c. So that is the velocity with which because here the kinetic energy, what is the energy of a photon whose momentum is the same as the proton whose kinetic, this is a proton kinetic energy that we have used here to calculate the velocity of the proton. Now once we have calculated that, we can move on to calculate its momentum, because in the question it is asked whose momentum is the same as the momentum of the proton. So we are going to calculate the momentum of the proton. P is equal to gamma times mu. This is a relativistic expression for momentum, where gamma has been found out to be 1.011 times, that is gamma, times the mass of the proton, that is in MeV over c squared units 938, times the speed that we have calculated in the previous step, that is 0.1449c. Here 1c and the c squared will cancel. The remaining units, momentum units, we are going to get in mgv over c units directly. So if we solve this, we get 137.38 mev over c. This is the momentum of that proton, and the photon has the same momentum. So photon momentum is the same as the proton momentum, having that kinetic energy, from where we have now got the proton momentum anyway. So photon momentum is also the same as this one, which is 137 rather, 0.38 mev over c. Now what is the energy of the photon? Energy of the photon. Photon is a massless particle, and its energy in relativity is given by E is equal to Pc. This is the total energy of the photon. When you know the momentum, this is the expression that is connecting those two things. So 137.38 MeV over C multiplied by C, the speed of light. So these two entities will cancel, so the energy can be directly written as 137.38 MeV. So this is the energy of a photon whose momentum is same as the momentum of a proton having an energy 10 MeV. So that solves the problem. Let's move on to the next one. Verify that the expression u over c is equal to pc over e, where u and c are the speed of an object and c is the speed of light in vacuum respectively, and p and e are the momentum and energy of the object. Right. So u over c is the same as pc over e. This is what we got to verify now. So if I just cross multiply the terms, I get EU is equal to PC squared. Here P can be expressed as gamma times mu. C squared is EU. So here the common factor is U. So the energy becomes gamma m c squared, which is the expression for total energy in relativity. So since this is true, this expression must have been true. So that is verified. Right, so let's move on to the next one. How much mass energy in joules is contained in a peanut weighing about 3 grams? How much mass energy we gain by eating about 300 grams of peanuts? The food energy of peanuts is about 100 kilocalories per 30 grams of peanuts. Compare these values and make a comment. So basically here, by consuming about 300 grams of peanuts, whatever energy we got to get, that must be equivalent to food energy. That's what we would normally expect. But we have to compare the values and see if it is so. Right? So first, how much energy is contained in about 3 grams of peanuts? Let's do that first. Energy is, we know that, is mc squared, mass energy equivalence equation. Here the mass is 3 grams. So mass is 3 grams, which is in kilograms, 3 into 10 power minus 3. So that is 0.003 kg. So we have energy as 0.003 times c squared, that is 9 into 10 power 16. So if you work this out, we get 0.027 into 10 power 16, which can be written as 2.7 into 10 power 14 um, joules. That is a unit, right, for energy here, because kg we have taken there. Kg and meters per second for velocity c. Right now, for 300 grams of peanuts, for 300 grams of peanuts, what would be the energy content in it? That is again using this equation mc squared. We can say 300 into 10 power minus 3 for kilogram conversion times this one. So that answer is going to be 2.7 into 10 power 16 joules. That is energy in this one. Right. Now food energy that is obtained by consuming about 300 grams of peanuts is given as, so that is not given here, it is given for 30 grams, right? So that is 100 kilocalories. Now 1 kilocalorie is 4184 joules. Therefore 100 kilocalories is I can write as 4.184 into 10 power 10 power 5 rather, 5 joules. So that is the energy equivalent of it. This is for about 30 grams of peanuts. For 30 grams of peanuts, this is the energy output. Here for 300 grams, we have to compare and see that that would be 10 times this value, that is 10 power 6 here, let us say. So for 300 grams, that would be 4.184 into 10 power 6 joules. That is energy. But in reality, we are not getting only this much, but we got to be getting 2.7 into 10 power 16 joules actually by eating that 300 grams. Why is this difference? This difference is due to the energy conversion capacity, or so to say the energy conversion efficiency. So our conversion efficiency is less, and that's why they're not getting all the energy content of the peanuts by consuming it. They're getting only a tiny fraction of it, so to say. Right. The next question, for an intergalactic space exploration, a spaceship of mass 10,000 kilograms needs to be accelerated to a speed of about 0.3 c. Calculate the energy needed in this case. Compare the value obtained to the projected annual energy usage on Earth, which is about 10 power 21 joules. So here, what is the rest energy of the spaceship? That's the first step we have to calculate. Rest energy of the spaceship. That is, let us call it E, which is equal to mc squared. That is 10,000 kilograms mass. So 10,000 multiplied by 9 into 10 power 16 joules. That is a 9 into 10 power 20 joules. mc squared, right? This is in kilogram units. So I can directly substitute this is about 10 power 4. So now the total energy we have to calculate, right? Because it is traveling at 0.3 c. So speed is 0.3 c. So the total energy is equal to gamma mc squared. We can calculate the gamma here. Square root of 1 minus u squared over c squared 1 over. that is gamma. So gamma is 1 over square root of 1 minus 0.3 c. So that is 0.09 here. And if we work this out directly, we can write gamma. Gamma is equal to 1.048. So that is the gamma I'm getting here. So if I substitute that here, 1.048 for gamma times the mc squared, which we have calculated to be 9 into 10 power 20 joules. And that is equal to 9.435 into 10 power 20 joules. That is the total energy of the um, spaceship. Now this is very high. Nearly, it is about 10 times only less compared to the annual energy usage on Earth, which is 10 power 20 joules. So our annual energy usage is only 10 times that energy required to put a spaceship at 0.3 C. So we need to produce either more energy, or we need to find other ways to uh, you know, put spaceships into space. So with the current technology, uh, it is very close to our annual energy usage. So I mean, it is still 10, nearly 10 here, right? So 10 into 10 power 20 joules is nearly the same as the annual energy, projected annual energy usage on Earth, which is 10 power 21. So nearly this is also 10 power 21, in fact. So that's pretty close. So unless we find ways to produce more energy on Earth, it isn't easy to put such spaceships in space. Right. The next question, the formation of sodium chloride from sodium and chlorine is accompanied with release of energy of about 4.2 eV. What is the increase in mass in unified mass units when a molecule of sodium chloride is dissociated into an atom of sodium and chlorine each? What percentage of error is made in neglecting this mass difference? So here, formation of sodium chloride and how much energy is released in the process is given. Now, what is the difference in mass? That's we have to find out first, right? Okay. So here, the masses in unified mass units of sodium and chlorine we have to write down first. So sodium is nearly 23 U, whereas chlorine is 35.5 U. In unified mass units is the masses for sodium and chlorine. Now, what is the difference in mass for this energy? So E is equal to, let's call that del mc squared here. What is the difference in mass? Del m. That is E over c squared. That is 4.2 eV is given in the question, over 9 into 10 power 16 joule. This is meters per second square, right? Meters square per second square. So this has to be converted into joules per hour. So I directly write 1.6 into 10 power minus 19 over this. And then I can directly do the math. I get this mass as about 7.467, let's say, into 10 power minus 36 kilograms. That is the mass. Now, one cube, that is atomic mass unit in unified mass units, is 1 0.66054 into 10 power minus 27 kg, and this is equal to 931.5 roughly into 10, no, nothing, this is just MeV directly, we can write MEV over C squared. This is in MEV over C squared, therefore you can write it. Right, so this value of del m that we have calculated here in U units is equal to, therefore, roughly 0.5 into 10 power minus 8. So that is what is required here. So the first part is what is the increase in mass when a molecule of sodium and chlorine, because sodium chloride is formed from sodium and chlorine. So we have taken individual masses of sodium and chlorine, and that is 58.5, because sodium plus chlorine together is 58.5 U. But this, for the sodium chloride, the formation, there is a mass defect of this mix. That is the difference in this mass to the actual sodium chloride mass. Based on what is given here, it is 58 U, because it is 0.5 into 10 power minus 8 U is the difference. So this is 58 point. I'm not fully writing this. This is got to be 0.5 to 10 power minus 8 U, so it's much less actually, right? So this difference, whatever is there, that is calculated here as this, and therefore in unified mass units, that is the difference in mass. Now, what is the percentage error if we don't we consider this mass difference? Because actual mass is less than the mass that should be obtained by adding the masses of the components, that is sodium and chlorine in this case. So the percentage error is the difference in mass, which is we have calculated here, over the actual mass. So that is going to be the percentage error. Percentage error in neglecting this mass difference is given by, to work out, we get about 8.55 into 10 power minus 9%. So that's a very small value, and that is why in such chemical reactions it is okay if you don't consider this mass defect. That is mass defect, I mean, by mass defect I mean the difference in the masses between the sum of the components and the actual total mass of the product. Right. Let us go to the next one. One of the fundamental nuclear fusion reactions involves two deuterium, right, deuterons, right, 2H nuclei combining to form a 4He nuclei. What is the decrease in rest mass? That's the first part. How much energy is released in this reaction? That is the second part. How many such reactions must take place per second to produce 1 watt of power? Now, what is the mass of this deuteron 2H nuclei? That is 2.014. Let's call that one mass of this one. Next, what about the helium 4He2? That is 4.002602 U. These are in U units, right? Now the reaction here in this case is 2H1 plus 2H1 combines to form 4He2 plus some of course this energy difference will be there, but this is actual equation. The first part we have to calculate what is the decrease in rest mass, that is del F. Let's call that. Now if we do 2 into 2H1 we are going to get twice this number. That turns out to be 4.028204. Now, if you see the helium mass here, that is less than this mass. So the difference del m is equal to 4.028204 minus 4.002602. So to find the difference, we get del m is equal to 0.025602. This is the mass difference between the masses of the individual masses of the 2H nuclei to the individual mass of the 4He nuclei. So the first part we have got the mass defect. The decrease in rest mass is this much. Now the second part, how much energy is released in this reaction, that is simply calculated by using E is equal to del m c squared in this case. So E is equal to, this is the U units, del m. So we have to convert that into equivalent MeV over c squared units. So we can write 0.025602 U, which is 1 U is 931.5 MeV over c squared multiplied by c squared. This, so c squared will cancel. So remaining thing is our energy unit. So E is equal to, finally we get in MeV, we get about 23.85, let's say, MeV. This is the energy equivalent. So that is the energy that must be released in one such equation. I mean, one such reaction rather, right? That is energy that is released. Now the third step is, how many such reactions have to take place for 1 watt of power? So 1 watt of power is, you know that it is equal to 1 joules per second. Now 1 electron volt conversion we have to do again. So it is 1.6 into 10 power minus 19 joules. Here we have, or we can do the other way, right? This 1 joule is equal to 1 eV over this number, 1.6 into 10 power minus 19. So that is going to be 0.625 into 10 power 19 eV is 1 joules. Now number of such reactions, therefore number of such reactions of the deuterium combining to give helium, number of such reactions that has to take place to produce 1 watt of power is this number, the conversion factor here that we got from joules to EV, over the actual energy that we calculated for one such reaction, which is 23.85 into 10 power 6. That is MeV we got. We are converting that to EV here by multiplying by 10 power 6. So we are getting about 2.62 times 10 power 11 such reactions. So this is the number. So that many reactions have to take place to produce 1 watt of power. So that many reactions occur in, for example, nuclear fusion reactors, thermonuclear fusion reactors, to produce such high quantities or large quantities of energy. Right, let's move on to the next one. This is about fission in uranium-235. The energy released in a nuclear fission reaction of 235U is about 200 MeV. How much rest mass, in kilograms is converted to energy in this fission reaction? So we got to get rest mass. Let's call that Lm. That is uh, energy over c squared, isn't it directly? So it is 200 MeV over c squared is 9 into 10 power 16 is 200 is converted into MeV, I mean joules, so it is 200 into 10 power 6 times 1.6 into 10 power minus 19. Now the energy is in joule units. Down below we have 9 into 10 power 16 m squared s minus 2. So the answer is going to be directly obtained in kilogram units, and if we work this out, that turns out to be 3.56 into 10 power minus 28 kilograms. Please work this out and verify whether you are getting the same. Right. The next problem, a radon isotope of 222 Rn is formed when a radium isotope 226 Ra decays by emission of an alpha particle, which is helium nucleus basically. So the radium nuclei weighs 226.0254 U, Rn weighs 222.0175 U. The alpha particle has a mass of 4.0026 U. Calculate the energy released in this reaction. Right, so reaction basically is 226 radium splits or decays into 222 Rn plus 4 He2, which is the alpha particle basically. Right. Now the individual masses are given. We are going to just use those numbers here to calculate the mass difference. So right side is we have to add these two masses, right? So the right hand side I write as 222.0175 U plus 4.0026. So if I add these two masses, I get 226.0201. And the left hand side is the radium mass, which is 226.02544 radium. Now the difference is basically mass of the left hand side minus mass of the right hand side. That difference if I calculate, I am getting 0.0053 U. The units are here U. So the energy equivalent of this mass is let us call that del mc squared. So that mass is 0.0053 U. 1 U is 931.5 MeV over c squared. Multiplied by the c squared, we are going to have directly the cancellation here, and then the energy equivalent E, let us call that as about 4.94 MeV. We're going to get in MeV directly by doing this multiplication. We are getting this number, and that is the energy. Right. Consider the decay reaction where chromium decays into manganese and an electron. What is the difference in MeV over c squared in terms of mass difference in this reaction? What is the maximum kinetic energy of the emitted electron? The masses of chromium and manganese nuclei are respectively 54.9279 U and 54.9244 U. So what is given here is the 55 chromium nuclei. Its mass is given as 54.9277 U. And then 55 manganese nuclei. The mass of that is given as 54.9244 U. The first part is mass difference we have to calculate between the left side and the right hand side. The left hand side we have only chromium, so it is 54.9277. The right hand side we have to add manganese mass with the electron mass. Electron mass we have to add here. This is for the right hand side. This is the left hand side here. Now the electron mass is, we know that the rest mass of electron, rest mass energy rather, is 0.511, because directly the electron mass has not been given in this question, so we have to do that. It is 0.511 MeV, rest mass energy. So I can say directly in MeV per c squared units, this is the rest mass. I have to convert this into U units, so to add it here, right? So that is 1 U is equal to 931.5 MeV over c squared. And therefore, if I do the conversion, I get the rest mass in U units is, for the electron, 0.511 over 931.5, that is 0.00055 U. So I have to add that here. If I add that here, I'm getting the total mass for the right hand side. Right? And that would be 54.92495 U. Now the left hand side is 54.9277 U. So we can see the difference in masses of LHS, that is the left hand side, and the right hand side RHS is equal to 0.00295. Right, so that is the difference. So we can say that it is 0. Or we can directly write 2.95 into 10 power minus 3 U units. This is the difference in masses, and that conversion now we can do in MeV over c squared as del m in MeV over c squared units by multiplying it by 931.5. We are getting about 2.75 in MeV rather, MeV over c squared. So what is the maximum kinetic energy? That is a question here that is being asked. What is the maximum kinetic energy? So Ke mass of the emitted electron. The remaining, the difference in these two masses must be maximum kinetic energy, and for that we can again use that the mass del m multiplied by c squared. The mass difference is 2.75 in MeV over c squared, rather multiplied by c squared, we get Ke max directly as 2.75 0.75 MeV. This has to be the kinetic energy of the electron. The remaining energy, whatever is the difference between the left hand side and right hand side masses, when it's converted into energy equivalent, we are getting the total energy, that will be the kinetic energy available for the electron in this reaction. Right. Let's move to the next one. What is the binding energy per nucleon in 12C6 isotope of carbon? The isotope has mass of exactly 12U. The masses of proton and neutron are 1.007276 U for the proton and 1.008665 for the neutron. So we know that the 12C6 has 6 protons and 6 neutrons. Right. So we have to say that 6 into this proton mass is 1.007276. That is going to be about 6.043602 on the this thing. 6.10086665 for the neutrons. So I'm adding the neutron masses totally. That is 051990. So if I sum these numbers, I am getting 12.095592 U. This is the mass that we expect to get by combining 6 protons and 6 neutrons to form the carbon nuclei. But the carbon nucleus here, it is 12C6 nucleus, has a mass of only 12 U. So the mass difference here is therefore 12.09, this number 5592 minus 12 U. Both are same U unit, so the difference is 0.095592 U. And therefore the energy equivalent is multiply this by, that is the total. In this case it is called the binding energy, right, to form the nucleus. So total binding energy of the nucleus 12C6 is 0.095592 times the energy equivalent of mass 1U, that is 931.5 over C squared multiplied by C squared, that is 89.044 MeV. If I multiply these numbers, I am getting this value. Now the question asks us binding energy per nucleon in formation of this 12C6. So that is going to be this total binding energy, which we have calculated in the previous step as this, over number of nucleons present here, that is 12. So if I do this, I am getting about 7.42 MeV. That is the binding energy per nucleon in this case. Right. The free neutron is known to decay into a proton, an electron, and a nearly massless anti-neutrino. This is known as beta decay, right? The total kinetic energy of the decay product is 0.781 MeV plus or minus 0.005 MeV. Show that this observation is consistent with the excess energy predicted by Einstein's equation E is equal to mc squared. Right? So here a neutron, free neutron rather, right, would decay to a proton, an electron, and an anti-neutrino, which is nearly massless. So this mass is negligible. Negligible mass it has. Now therefore the two masses that are of importance is the proton and the electron mass on the right hand side and the neutron mass on the left hand side. So we can add the LHS same. LHS mass is the neutron mass, which is m is equal to, let us not write m, I think mn maybe we can write mn is equal to 1.008665 U. For the right hand side, the proton mass is 1.007276, right? U plus the electron mass, which we calculated in one of our problems earlier in MUV, U units, that is from 0.511 MeV over c squared units, we can convert into U units as 0.0005486, both cases U. So the right hand side, if I add, I'm getting 1.0078246 U. The left hand side is just this. So the difference between the left hand side and the right hand side masses, we call that LM, is 0.0008404 U. Now 1 U is equal to 931.5 MeV over c squared. So if I use the conversion factor, I'm going to get my del M in directly MeV over c squared units. And that is 0.783 MeV. If I do this math. Now this number is in the zone, right? This number is within this range that is given here. 0.781 MeV plus or minus 0.0. Because here, since the error is given here, we can say that this range is 0.776 MeV to 0.786 MeV. That is the range that is given in the question for the kinetic energy of the decay products. And that kinetic energy, here we are getting from the mass defect as 0.783 MeV over c squared. Of course, if you do the kinetic energy, you will multiply with this and you get, yeah, this is MeV over c squared, right, mass. So if you multiply by c squared, you will get this energy range. So that range and this will match. So it is in the zone or in the range, and therefore we can say that this observation is consistent with the excess mass energy predicted by E is equal to mc squared equation. Right. So that completes some of the problems that we wanted to solve on the concept of mass energy equivalence in special relativity. Thanks for watching.